some would say. So he's going to tell us about constraining inflation and we will be going off for a few minutes. If you want to join, please.
All right, thanks, Amir. So today I'm going to talk about some work that I've been doing on high energy physics of inflation and analysis in WMAP and Planck. This is mainly going to be a talk about non-Gaussianity, primordial non-Gaussianity. So I'm going to introduce inflation, talk about why primordial statistics based on testing Gaussianity of the fluctuations are interesting probes of the physics, and then talk about statistics a little bit, and then present results from WMAP, and talk a little bit about Planck. Okay, so first I'm going to just introduce inflation. So inflation was invented largely to solve the horizon problem. When we look back at the early universe via the CMB, we see a nearly isothermal surface of last scattering, suggesting that the universe was initially in thermal equilibrium or close to it. If we plot the CMB without mean subtraction, then the temperature between the coldest and hottest points in the sky just differs in the fourth decimal place. But the causal horizon, when the CMB was generated at last scattering, is much smaller than this. It's around, say, 250 megaparsecs, corresponding to an angle of around 1 degree on the sky. Points that are further separated than that have never been in causal contact. In fact, with modern data, we could state the horizon problem in an even stronger form. If we plot the angular correlation function of the fluctuations, it's non-zero at separations above 1 degree, which proves, at least statistically, that points separated by outside the causal horizon depend on each other statistically. The fluctuations over here, their detailed statistics depend on what the fluctuations over here are doing. So a way of to be more quantitative about the horizon problem, if we plot 1 over AH, which is the co-moving distance that light travels in an e-folding, the causal horizon would just be the integral of this. The Friedmann equations imply that that evolves with scale factor A if we plot on log-log scale. That the slope on this plot is 1 plus VW over 2, where W is the equation of state of the universe, the total pressure divided by the total energy density. So if the universe is filled with either non-relativistic or relativistic matter, the slope is always positive. The causal horizon is always increasing with time. And at early times, if we integrate this, we always get something small. This way of plotting the horizon problem makes it clear that in order to solve it and get a large causal horizon at early times, we want to assume that the usual lambda CDM expansion history is preceded by an epoch where the equation of state is less than -1/3 to make the slope negative, which will lead to a large causal horizon in early times. So we need some source of negative pressure in the very early universe. So what could be the physical source of negative pressure? One simple possibility is to just assume the existence of some scalar field, some new scalar field that wouldn't be part of the standard model, with some potential that gives it a large energy density. For this to give rise to inflation, there's a technical requirement that the potential be flat. One way of quantifying this is just to plot the log derivative of the potential. Call that quantity epsilon. That should be much less than 1 in order to lead to many e-foldings of inflation. Otherwise, the scalar field would just roll to the middle too fast. This generates negative pressure in the equation of state for this scalar field. The flattest condition means that you're potential dominated. And if epsilon is small, then the equation of state is equal to -1, and you get inflation. By the way, the observational upper bound on epsilon, around 10 to the -2, comes from the non-observation of gravity waves in large-scale CMB temperature by WMAP. Okay. Now, what's really amazing about inflation is that the same, if we assume that there is some source of negative pressure and close to exponential expansion in the early universe, that can naturally explain the existence of perturbations to start the evolution of the universe and their statistics. So it's a physical prediction of general relativity plus quantum mechanics that in an inflationary background, microscopic degrees of freedom get quantum mechanically excited. So to explain why that happens, let's just consider a toy example, which is a little bit less complicated than the full inflationary physics, but contains all the qualitative features. A massless test scalar field, meaning that its fluctuations don't backreact and change the metric, minimally coupled to the metric. So this minimal coupling means that if you write the action for this scalar field, we have a factor of a squared where a is the scale factor. We have explicit time dependence on the Lagrangian. Each Fourier mode, it's easy to start from this action and show that each Fourier mode of the field then behaves as an independent one-dimensional harmonic oscillator with the time-dependent Hamiltonian shown in the slide. So eta here is the time coordinate. That's conformal time during inflation. Inflation begins at eta equals minus infinity and ends at eta equals 0. In writing this Hamiltonian, I've reverted to usual quantum mechanics notation where the coordinate is x and its conjugate momentum is p, but the x that we're talking about here is really sigma k, one Fourier mode of the scaling field.
This is the action that you're representing?
That's right. So this is the first line is the action. That action is quadratic. So each k mode of the field obeys an independent equation of motion. And the last line is a Hamiltonian for that single degree of freedom.
Yeah, but within the action you have a squared, so you should have your negative 4. Just a technical remark.
This is definitely right. The scale factor is 1 over h eta.
No, but in the first line of the action, right? You're writing your d4x squared root of minus p.
Oh, you want to have square root minus. There's a square root minus 2, which is eta to the 4th, and then there's a g upper mu du, which is eta to the minus 2. This is the action for a minimally coupled scalar field. Okay, so if we just pretend this is Schrodinger equation in quantum mechanics and consider this Hamiltonian, then it's easy to show the following. This is, at a fixed value of eta, this is just the Hamiltonian of a harmonic oscillator. The time dependence means that at early times, when eta is much less than 1 over k, I suppose that should be minus 1 over k. Then the time dependence here is adiabatic, meaning that the rate of change of the Hamiltonian is small compared to the natural time scale of the oscillator. That means that if we start the system in its ground state, this is the so-called Bunch-Davies vacuum with no particles, then the wave function will just stay locked in the ground state as the width of the oscillator changes. Toward the end of inflation, when eta is at late times, then we're in the opposite limit where the Hamiltonian is changing so quickly that the wave function can't adapt. And the functional form of the wave function in position space is essentially frozen while the Hamiltonian changes. This transition between the two behaviors, so in particular, that's an excited state. What the Gaussian wave function corresponding to the ground state for one value of eta will not be the ground state at a different value of eta at the instance of excited states. The transition between the two behaviors happens when the causal horizon during inflation becomes equal to the wavelength of the mode, which is called horizon crossing. So at the end of inflation, we have an excited state. The wave function is Gaussian. That's actually true at all times. This Hamiltonian is exactly solvable, and that turns out to be true. We have large occupation numbers, which means that we can treat each mode of the oscillator as a classical randomly distributed variable with a Gaussian PDF. This form of the wave function shows that the variance of that Gaussian goes as 1 over k cubed. Each Fourier mode has a variance proportional to 1 over k cubed, which is what we call scale invariant power spectrum. In this example of the massless test scalar, we end up with a Gaussian field. Each Fourier mode is an independently distributed Gaussian random variable with a scale invariant power spectrum. That is what we need to start the universe with statistics that will be consistent with the CMB large-scale structure, a wide range of precision cosmology observations. There's one more ingredient, which is that we need to convert fluctuations in the inflationary sector, say massless test scalar, or there are other possibilities, to standard model particles. So simplest possibility is that the scalar sigma is just the inflaton itself, and that just decays to standard model particles in a way that just converts the energy density, fluctuations in the energy density of the inflationary sector into fluctuations in the energy density of standard model particles. The preceding slides have sketched a model of inflation where we've just added one field, assumed a slow roll potential with large energy density in the early universe, generated fluctuations in that inflaton field quantum mechanically, and translated them into the standard model. In this simple model of inflation, it was first shown in a very seminal paper by Malsena that deviations from Gaussianity are unobservably small. Now, this has depended on several assumptions that I want to make. This conclusion has depended on several assumptions that I want to make explicit. One is the assumption of that only one field is important, and that field is the inflaton itself in determining the initial conditions of the universe. That matters because the flatness condition, the conclusion that non-Gaussianity is small, is related to the flatness condition. If you could adjust the potential, make it steep, then you could get large non-Gaussianity without ruining inflation. Another assumption here is that reheating is homogeneous, that it happens in the same way everywhere. We'll talk about exceptions to that in a minute. And finally, that the inflaton Lagrangian has this simple form, just a minimally coupled scalar in a potential. One comment here is that the model, this is the simplest model of inflation in the sense that it's simplest for us to write down and calculate. But we'll see that models of inflation that come from UV completions, say models that are proposed in a stringy context, typically are complicated. So this might be the simplest model for us to think about, but not necessarily the simplest model to fit in with the rest of physics. Okay.
So there's already a little inconsistency in your simplest model because you've got your inflaton Lagrangian, but then you also say that the inflaton must gain standard model particles. So in your inflaton Lagrangian, you've got to couple the inflaton.
That's
so
right.
that it can decay.
Yeah, that's true. If you literally had this potential, then you would just have a universe that is all inflatons forever.
And yeah, that can lead to non-Gaussianity and stuff, to speeder models of inflation, and then you'll find being company work done, is that just the mere fact that the inflaton has to couple to other fields, standard model fields, can then lead to kind of a perturbation feedback, that perturbations in the inflaton couple to another field that then couple back to the inflaton to get non-Gaussianity that way.
That is right. That's right.
That depends a lot on the couplings.
Right. No, it depends on the couplings. But yeah, the point is that you can't have an inflaton Lagrangian that's just, the inflaton has to couple to the other particles, or else it can't decay.
Yeah, agreed. Okay. So in the next few slides, I'll introduce some non-Gaussian models. The model that I think is conceptually simplest, this wasn't the first mechanism introduced, but just conceptually simplest, is modulated or inhomogeneous reheating. So let's suppose that reheating doesn't happen in the same way in all parts of the universe, but that its decay rate, gamma, is controlled by some other field, sigma. So you could just write the decay rate at a point x as some sort of mean decay rate plus terms just corresponding to the other series in sigma. And then sigma will at the end of inflation will have perturbations, if for no other reason, because there's this standard mechanism of quantum mechanical generation of perturbations in all fields during inflation. And so this leads to an initial perturbation. You could think about it as perturbation in the energy density at fixed, after a fixed number of e-foldings of expansion, or the way that I've written it here, parameterizing it by the adiabatic curvature fluctuation, you're thinking of going to the gauge where time slicing is surfaces of constant energy density. You're keeping track of how much each part of the universe is expanded. Anyway, parameterizing it in terms of zeta, this just leads to an initial curvature fluctuation in which the initial fluctuations are proportional to sigma and include quadratic and higher terms. So we can write the initial curvature fluctuations as a leading piece which is Gaussian, plus additional terms which are quadratic and higher powers of the Gaussian piece. That introduces non-Gaussianity. So this is the so-called local model. One way to get it is by inflaton decay that's mediated by another field. More generally, it arises in models where non-Gaussianity is generated by local physics operating after horizon crossing, after modes that we observe in CMB have become much larger than the problem horizon during inflation. So modulated reheating falls into that category. Some other examples in the literature, I won't really have much time to do justice to the physics, since I mainly want to talk about data analysis in this talk. Another example that you may have heard of is the curvaton model, where the source of curvature fluctuations is not the inflaton, but some spectator field that doesn't have to have a flat potential and can have significant levels of non-Gaussianity. There's also alternatives to inflation, the so-called ekpyrotic model. It's been argued that non-Gaussianity is generic in these models. This is a two-field model where the physics context is very different from slow-roll inflation, but for purposes of calculating these perturbations, it's basically a similar mechanism where there's two fields. One of them is a spectator field. It can be non-Gaussian. It sources the initial curvature perturbations. So in models where multiple fields are important, if you do not fine-tune anything, then you naturally find values of this FNL parameter, parameterizing the level of non-Gaussianity, between 1 and 100. In some of these cases, the non-Gaussianity is of order 1, and in others, there's factors of 1 over a slow-roll parameter that makes it kind of naturally of order 100. By the way, the parameterization here is such that because zeta is a field where the initial fluctuations are of order 10 to the minus 5, FNL of order 1 really corresponds to non-Gaussianity, which in rescaled units would be of order 10 to the minus 5. So FNL of order 1 is really a very, very tiny deviation from Gaussian statistics. Nevertheless, jumping ahead a little, statistical errors currently around the 1 sigma error on FNL, on the local FNL is 21. And in the future, could conceivably get down to order 1. So we have the observational power to tell whether single field, in the future at least, to tell whether inflation just involved a single degree of freedom, or whether multiple fields are important, at least if nothing is fine-tuned. Another way to generate non-Gaussianity is just to consider a scalar field which has interaction terms. In the toy example that I talked about earlier, we just assumed a quadratic Lagrangian. But if you put in an interaction term, and I'll talk about the physical motivation for doing this a little later, in particular why I chose this kind of weird form of the derivative, the time derivative cubed, then that leads to non-Gaussianity. To leading order in this coupling constant, all the non-Gaussianities in the 3-point function. And the 3-point function is easy to calculate by the standard procedure in quantum field theory. We can exactly solve the dynamics if we just keep the quadratic part of the Lagrangian. And then we just do perturbation theory in the cubic and higher terms and organize the result as a sum of Feynman diagrams. So for this example, the 3-point function, the 3-point correlation between 3 Fourier modes of the sigma field, is just given by this simple tree-level diagram. You can work out the Feynman rules and write the 3-point function in a simple form. We proved in the reason why I chose this particular interaction, the time derivative of sigma cubed, is that there's a theorem that we proved in this paper from a few years ago, a classification theorem that states that, so I want to make the assumptions explicit here. One assumption is that non-Gaussianity is single field in the sense that the initial curvature perturbations just depend on what the inflaton is doing and not on any other fields, any spectator fields or anything. Another more technical assumption is that the inflaton Lagrangian can't have weird explicit time dependence, like if you had a phase transition or transient features in the inflaton potential, or a potential that had highly oscillatory component. All of these are kind of loopholes that came out after we wrote our papers, so we're probably not clear enough about our assumptions. Then it can be shown that the most general 3-point function that you can get in this single field context is a linear combination of the 3-point functions that you would get if you had a test scalar with either a sigma dot cubed interaction or this interaction which sigma dot times 2 spatial derivatives of the input field. So this is not at all obvious. It took a lot of machinery to prove this. The main technical tool is the effective field theory formulation of inflation that I won't hold enough time to discuss in the talk. Okay. So single field inflation naturally has 2 parameters. If we think of the 3-point function at the end of inflation as being something that's defined by closed triangles in Fourier space, so those momenta have to add to 0 by momentum conservation for the 3-point function to be non-zero. Then the single field shapes, I said in the last slide I stated that there are only 2 shapes of the 3-point function associated with single field inflation. Look qualitatively similar. They're both peaked on equilateral triangles and small in this squeeze limit that has a special, where one of the wavelengths becomes very long compared to the other 2. That squeeze limit has a special significance, for example, in large-scale structure that I'll talk about later. The local shape that arises in multi-field inflation, that's characteristic of multi-field inflation, on the other hand, has signal to noise that's dominated by squeezed triangles. So the single field shapes are distinct from the local shape and should be thought of as more or less independent parameters. One more thing before I get to the data analysis. The 2 single field shapes are fairly similar to each other and are roughly 90% correlated. Correlation defined in an observational sense by the correlation coefficient between the CMB estimators that estimate their amplitude. They're peaked on equilateral triangles and small in the squeeze limit. It's convenient. However, when you have this 2-parameter family, you can always orthogonalize and find a linear combination which is orthogonal to either one of the guys that you started with. So for the data analysis, rather than keep track of the large correlation coefficient between the 2, we found it convenient to go to an orthogonal basis. So we defined these numbers here just come out of a numerical calculation. We just calculate this matrix that orthogonalizes the basis. So in practice, we work with our basis for single field inflation consists of an equilateral shape, which is peaked on equilateral triangles, small in the squeeze limit, and also small for so-called flattened triangles, shown in the central column, where the area of the triangle becomes small. The orthogonal shape changes sign. It's positive for the equilateral triangles, negative on the flattened configurations, all the single field shapes are small in the squeeze limit. So that's just convenient for the data analysis to have parameters that are more or less uncorrelated. Okay. The next part of the talk, I'll talk about data analysis. So the logical sequence here is that we start with some model of inflation. There's usually some diagram that we calculate to find its observational signature of the 3-point function. So we calculate the curvature 3-point function, the correlation function of 3 Fourier modes of zeta at the beginning of inflation. To translate that into something that we observe in the CMB, we need to feed that through all the linear physics that is in CAM, all the linear physics that determines the observed CMB fluctuations linearly from the initial curvature fluctuations. Once we've done that calculation and we have a 3-point function between ALMs of the CMB that we're looking for, we then have to construct an estimator that will feed in a CMB map and output some sort of statistical estimate for the amplitude of that 3-point function. And then finally, there are some technical issues evaluating this estimator practically on WMAP. So let's talk about each of these steps. So the first thing that we noticed when we started doing this is that the general case is just not computationally tractable. If you try to be too general, this just doesn't work. So if you just try to compute the CMB 3-point function from a general curvature 3-point function, then you would end up, you can write down a formula for this. All that's going on here conceptually is that you just have 3D to 2D projection. You're just projecting the 3D modes of the curvature field onto the surface of last scattering in kind of a complicated way that involves propagation of sound waves and all the acoustic physics of the CMB. But numerically, it just turns out that this is, for each triple L's, you have to do this 4D oscillatory integral, which is very computationally demanding. There are Bessel functions in here. You need many, many points to do that integral. Even just calculating one 3-point configuration is really numerically difficult. You have to calculate this for every triple multiples in CMB. So even just getting started with the analysis by calculating the CMB 3-point function would be really, really difficult. And then if you try to be completely general and write down the optimal estimator for estimating an arbitrary CMB 3-point function from data, this turns out to have be a sum over multiples of the CMB that contains L max to the 5th terms. So with L max around 1,000 in WMAP, that would be 10 to the 15 terms. Too slow to do this, even with a large computer, especially given that we need to do this with many Monte Carlo simulations to set statistical errors. However, what originally seemed like kind of a miracle of algebra, like a coincidence, is that if you use a physical shape and just plug and just go through this chain of general formulas with a physical shape plugged in, then you always seem to end up with something tractable. So, and going back to the example that I showed earlier of this pi dot cubed interaction, if we evaluate this Feynman diagram, it naturally, the result's naturally presented as an integral over the time where the interaction happens. For reasons that I'll get into later, let me just not do that integral and keep the eta integral on the outside. If you work through all the algebra, then you find that the estimator which estimates this 3-point function from data can be written in this form where part of the operations are done in real space, pixel space, rather than harmonic space. And you can make this computationally affordable through use of fast spherical transforms. So in this case, there are some integrals over conformal time during inflation, and also the R coordinate here, the R integral here, is over distance between the surface of last scattering and us. That's not perfectly sharp, that has some width, but the integrals peak near the surface of last scattering. Anyway, the integrand is just the cube of some map in pixel space. You do a fast spherical transform to get this map in pixel space and just cube it. And so I eventually understood. We wrote 3 data analysis papers before I sort of realized that this isn't really a coincidence. It's just related to the fact that when you evaluate a Feynman diagram, you always end up with something which is factorizable in the 3Ks, is a product of functions in the 3Ks independently. That's true even for higher point diagrams, because you'll have some outer integrals over times, and then when we evaluate a Feynman diagram, the integrand is just the product of propagators. So at every vertex, we just have the product of all the propagators, which just depend on the k's going in. And so this would generalize to any tree-level diagram. We're writing a paper where we do this for the 4-point function. If you draw any tree diagram, then you just naturally end up with a CMB estimator for estimating the amplitude of that diagram, where the combinatorics of the estimator correspond to the combinatorics of the Feynman diagram. Each vertex corresponds to a product of maps in pixel space, and each line in the diagram corresponds to a spherical transform and multiplying by some weight in harmonic space. In practice, we think that the right approach to these computation problems is just to go back to the physics. There's other approaches in the literature that are based on expanding things in orthogonal polynomials and things like that. But our perspective is that the physics just naturally tells you what to do. Okay. There are a few computational problems. That was sort of a conceptual problem. There are a few computational problems. One is that even though we have this formula for the estimator, which is fast, it has some outer integrals over these variables eta and r. And in practice, we're going to approximate those integrals by finite sums. But naively, you need a lot of points to do those integrals, and that leads to high computational costs. So for each point in the eta r plane that would be needed to evaluate this integral, that leads to one pair of spherical harmonic transforms that you have to do when you evaluate the estimator, CMB estimator on map. So we found this fun general optimization algorithm. The general form of the algorithm is like this. Suppose you have some estimator that you want to evaluate on data, and that it can be written in as a sum of n terms, where n is large. And you know the covariance matrix, so you have some estimate for it, the covariance between the individual terms in the estimate. Then, using a bunch of linear algebra tricks, we can find a minimal subset of the terms, such that all the other x hats that aren't in the subset are highly correlated to a linear combination of guys in the subset. So this lets us go through and, up to some controlled approximation, replace each of the xi hats in the original estimator by a linear combination of guys in the subset, and write the original x hat as a sum with many fewer terms. So this optimization algorithm is generally very useful in any sort of statistical situation where you're trying to apply some estimator that can be written as a sum of many terms that is computationally expensive. I've used it in a variety of contexts since then. Specialized to the FNL estimator, it means that we can start by writing this estimator as an integral with many points in the eta r plane, and this using the numerical linear algebra, we can replace it by a small number of points with optimally determined weights. Here's an example. If we start with this pi.cube shape that I talked about before, we originally write down an unoptimized estimator where we just densely sampled the eta r plane with, say, 80,000 points, which is sort of naively the number of points that you might think that you need. If we apply this optimization algorithm, it somehow replaces this by 86 points. You can see that these are concentrated near the surface of last scattering. The R here, so the distance to last scattering in the traditional model we were using was 1.41 times 10 to the 4. So the optimization algorithm automatically figures that out. 86 times 2 spherical harmonic transforms is relatively fast, and that's good enough to evaluate this estimator efficiently on WMAP.
How do you do that? How do you form the linear combination? How do you find the weights in the linear combination?
More or less the way we do it is we first go down the diagonal of the matrix and pick the guy that would help the most if you could only use one. And then there's a trick for in n squared time, maybe you think you need n cubed, but there's a linear algebra trick. In n squared time, you can automatically update the covariance matrix to orthogonalize everybody else. And then you pick the second guy that would help you the most after projecting the first guy out, and so on. So it's sort of a greedy, computer science language, it's sort of a greedy algorithm. It takes sort of the locally best choice at each stage.
And when do you stop?
So the criterion for stopping is that you have approximated the original shape closely, where close is defined in the sense of observational distinguishability. So we stop when you are within 10 to the minus 6 of the original shape, which would mean that there's no experiment you can do. This is always up to some Lmax, right? That can distinguish the original shape and the approximated shape better than one part of the 10 to the 6.
I'm sorry, what is 80,000?
This is a little ad hoc. We don't work very hard on optimizing this since the optimization algorithm will get rid of all this. But this is just if you plot the integrand as a function of eta and r, and just use kind of a naive criterion for guessing what sample you would need in the eta r plane. And this is okay.
And sorry. So C inverse ALM means pre-Weinstein map.
Yeah, right. So I'll talk about that next. So this is, I want to sort of minimize discussion of this, but this was a huge technical problem that I have to have at least one slide since I spent like 6 months of my life on this. The optimal estimator calls for C inverse A, which I didn't really define before, but this is what it means. If you think of the original CMB map as a vector, So you can imagine one number for each pixel, and so collect those into a vector whose length is the number of pixels in the map. Then to evaluate the optimal estimator, you're required to compute C inverse A, where the matrix C is the sum of the npix by npix matrices corresponding to the noise covariance and signal covariance. So the reason this is hard is that the noise covariance is diagonal in pixel space. At least that's a good approximation in WMAP. There's noise in each pixel, but distinct pixels are correlated with each other. The S is the signal covariance, the intrinsic correlation function of the CMB, which is diagonal in harmonic space. If you had to invert either of these matrices individually, it would be trivial, and then you just go to the basis where you're diagonal. But when you sum them, there's no basis where the inversion is trivial, and this appears to require inverting a matrix whose size is the number of pixels in the map, and so we found a fast algorithm for doing this, which is similar to, if you've seen multi-grid algorithms for elliptic different partial differential equations. For example, Laplace's equation. You can describe Laplace's equation in the same way. If you want to find a map X whose Laplacian is some fixed map A, then that formally looks like inverting an operator whose a matrix whose size is the number of pixels in the map. But there are fast techniques for solving this based on iterating the solution at different resolutions, going up and down in resolution in some optimal way. These algorithms generalize to this context, and we can do this inversion. We can't compute the C inverse as a matrix, but we can implement sort of a black box procedure where you put in a CMB map and you get C inverse times the CMB map out. In about 15 core minutes for WMAP, and then Planck is running at it in 4 hours, which is fast enough. Okay. So those are all the technical ingredients that we need to start with a model, evaluate the diagram, calculate the 3-point function, construct the optimal estimator, we have C inverse. Now we just sort of need to plug in the WMAP data, and the next part of the talk I'll give results from WMAP. So the local shape, first, this is the shape that's characteristic of multi-field models. The first optimal constraints were reported in this paper that we put out a few years ago, this was in 2009. At the time, there was a lot of interest in this, since there were a variety of results in the literature. I listed some results here which are did more or less the same analysis and found a 1 sigma result, a 3 sigma result, and a 2 sigma result. So you kind of get any number of sigmas that you wanted. This measurement really resolved this controversy. The optimal estimator, one thing that's good about the optimal estimator is that it has the smallest error bars. But the other thing is that it disambiguates the analysis. The difference between these analyses that were in the literature is that they just made different arbitrary choices of weighting in L or weighting different parts of the map. And neither of them was wrong. But in a situation where you're significantly suboptimal, and the analysis always depends on arbitrary choices, and so there's no real criterion for deciding which one of these results is correct. So the optimal estimator just has no pre-parameters and ensures uniqueness of the result. It just sort of boils everything down to, in this case, just a result that's just shy of 2 sigma. So our perspective is that, and then this pipeline, this was for WMAP 5, but since then I've joined the WMAP team and we use this optimal pipeline in WMAP 7. The result is still consistent with FNO equals 0, and so current data seems to be consistent with single field inflation. Planck will reduce this error bar down to about 5, which will be really interesting to see. All right, the single field shapes. So these are the equilateral and orthogonal shapes, which are an orthogonal basis for non-Gaussian 3-point functions that you get if you have interactions of the input function. So the error bars here are both about 1 sigma away from 0. In this plot, the ellipse is roughly aligned with the axes. There's a little bit of correlation here, but we have roughly decorrelated variables. This plot is sort of a master analysis of single field inflation, which can be compared to a particular model. So I just we have a lot of different case studies for this, but I'll just discuss one. So dBi inflation is a string-motivated model of inflation where the inflaton, the scalar field that drives inflation, corresponds physically to the distance between two grains in a compactification. I can't really talk about this model in much detail. Understanding all the details is probably a full-time job, but the effective action at low energies for this model, what's relevant for calculating stuff during inflation, is this weird-looking Lagrangian where the kinetic term is non-canonical. There's this weird kinetic term, this is the dBi square root. The way the physics works is that that weird kinetic term sets a speed limit on how fast the inflaton can roll down the potential. The potential in these models doesn't have to satisfy a flatness condition. It can be steep, but inflation nevertheless lasts for many e-foldings because there's a speed limit to how quickly you can move down the potential in one fold. These models generically predict non-Gaussianity. Because they're single field models, our classification theorem applies, and we can parameterize the level of non-Gaussianity by a value of f(n) equilateral and f(n) equilateral. By the way, it's one thing that's interesting is that because the Lagrangian looks so different than the Lagrangians we were writing down before with standard kinetic terms, it's not at all obvious that the non-Gaussianity that you would get in this model would match with anything that you would get out of the usual setup where you have a standard kinetic term plus some cubic interactions. But there's after several changes of variables, you can see that that's true. Non-Gaussianity in this model depends on one parameter, which is a sound speed during inflation. And so our WMAP constraints, if you take these formulas for f(n) equilateral and f(n) orthogonal, evaluate them on the plot that I showed in the previous slide, and you can translate that to a constraint on the microphysical parameters of this model for the sound speed. One interesting thing about this model is that it has a level of non-Gaussianity that looks like 1 over the sound speed squared. But this model also predicts tensor modes proportional to 1 power of the sound speed. Since these are sort of inversely proportional to each other, you can have small non-Gaussianity or small tensors, but not both. And it turns out that if Planck fails to observe either equilateral non-Gaussianity or large-scale tensor modes, then this class of models will be ruled out. So Planck is getting to the point where non-Gaussianity can really discriminate between different qualitative classes of models and rule things out entirely. Okay. For the last 5 minutes, I'll talk about gravitational lensing a little bit. So this was fun. So gravitational lensing, I'm going to talk about something that has nothing to do with primordial non-Gaussianity, but can be analyzed using the same type of statistics. So the CMB is lensed. When we look back to the surface of less scattering, geodesics are deflected by large-scale structure, and this just remaps hot and cold spots while conserving surface brightness. So it does not, for example, generate new anisotropy out of the 2.7 Kelvin monopole of the CMB. It just moves existing anisotropy around. Gravitational lensing induces a 3-point correlation function between 2 powers of the CMB and 1 power of the projected matter density or the projected potentials that are doing the lensing. So I want to just describe, for the sake of pedagogy, intuitively why you would get this correlation. If you imagine that you look through a large-scale overdense region, then that will magnify, stretch out the CMB hot and cold spots. That means that the acoustic scale, the characteristic correlation length of the CMB, will be shifted to a larger apparent or angular separation. And if you measure the CMB power spectrum, looking through an overdensity, you will see the acoustic peak shift to lower power. Conversely, if we look through a large-scale underdensity, then you'll see a different CMB power spectrum. The acoustic peaks will shift to higher power. With this type of correlation, where the CMB power spectrum is not the same everywhere, but slightly modulated by the large-scale matter overdensity, is a 3-point correlation. We're saying there's a correlation between CMB power, which is quadratic, and 1 power of the matter density. So we get this 3-point function, and it shows up in squeezed triangles because we're talking about small-scale CMB hot and cold spots at a long wavelength matter density that's doing things like a large lens. That type of configuration, a large lens and small hot and cold spots, turns out to have high signal lengths. So even though this is not primordial, our data analysis machine we applies to any 3-point function, and we can evaluate this 3-point function on data. For the 2 CMB legs, we use WMAP, and for the matter leg, we use radio galaxy counts from NBSS. That's a highly correlated tracer of the projected CMB lenses. And so this allowed us to sort of the spin-off of the primordial non-Gaussianity work. Allowed us to report the first detection of CMB lensing, at least using this cross-correlation tracer, at a statistical significance of around 3.5 sigma. There are now there have been more detections reported since then. For example, ACT has a 4 sigma internal detection that doesn't use the cross-correlation tracer. This was where the first detection came from. Things that we're doing to continue this work. So I'm working on the WMAP 9 analysis. One new thing there is that the C inverse weighting can be used to improve any sort of endpoint function. I talked about 3-point examples, but can also be applied for the power at n equals 2 for the power spectrum itself. So using C inverse weighting, we're going to improve the error bars on the power spectrum, which is the main scientific output of WMAP. Correspondingly improving the errors on most cosmological parameters by 10 to 20%. I'm currently working on the Planck collaboration to evaluate some of these statistics in Planck, which has been really addictive to take these old WMAP programs and run them on Planck and just see error bars magically come out that are smaller by a factor of a few. Gravitational lensing, for example, is 30 sigma in Planck, but it's only 3 sigma in WMAP. And a paper that we're about to put out is doing all of this for the 4-point function. There's some examples of models where the non-Gaussianity shows up first in the 4-point function. To give one example, it's been argued that in supersymmetric models of inflation, where the superpartner of the inflaton has a non-flat potential, there's no symmetry protecting it from being non-flat, then you should naturally expect a 4-point function from the type of diagram shown on the right here, where 2 inflatons exchange an inflaton superpartner. So that's it for today. I had some more slides about large-scale structure, but since I'm at 4 o'clock, I'll stop here. Thanks.
Can you comment a little bit more about where the statistical improvements in Planck are coming from? More pixels?
Yeah. So Planck is just adds smaller angular scales. So the level of improvement, you notice the level of improvement depends on the shape. For example, gravitational lensing improves by a factor of 10, whereas the primordial shapes improve by a factor of, say, 3. That's because gravitational lensing is just more weighted to orthogonal.
And just as an off-the-wall question, one can imagine other things fluctuating during inflation. I mean, suppose this has something to do with the development of the gauge hierarchy, right? I mean, so perhaps the scale of these integrating fluctuates by 1 particle minus 5, that's something like that. I mean, to what extent could you use the CMB combined, I guess it would need some type of large scale structure as well to maybe test something like that.
Okay. I think the generic statement is that multiple fields interact somehow during inflation. You generically get ethanol at least of order 1, provided that you don't have a situation where only one field ends up setting the curvature fluctuations at the end. So if the inflaton just dominates the energy density the whole way through, even through the heating, then it just gets washed out. But if that doesn't happen, then generically you get back in zero or 1. Now, whether that shows up first in the CMB or in large-scale structure is a trickier question. I didn't get the chance to talk about large-scale structure in this talk. It's really a subject of a separate talk. But there's been some really pioneering work done largely here, or mainly here, for constraining this type of primordial physics from the behavior of large-scale structure on large scales. For the local shape, and whether the CMB is the best discriminator or large-scale structure is the best discriminator, depends really sensitively on the shape. For the local shape, for the local FNL, large-scale structure will eventually be better, no question, than Planck or even a futuristic CMB experiment. But for example, for the equilateral shape, there's essentially no constraint from large-scale structure. And this is because large-scale structure is really more of a general test for whether the initial conditions are the same, statistically the same in widely separated parts of the universe or not. Whereas the CMB really lets you measure the same number of degrees of freedom that you have in the initial conditions, and you have full shape discrimination. You can effectively evaluate a Feynman diagram on the CMB by connecting the legs of the diagram to 1 power each of the CMB. Large-scale structure is more of a general test, and the extent to which that makes you sensitive to primordial non-Gaussianity depends on whether the endpoint functions that you're considering have large limits in certain limits. For example, if you have a 4-point function that becomes, I'll sneak ahead to one of my slides that I didn't show. So if you have endpoint functions that become large in the limit where one of the sides, these are 4-point functions, goes to 0, one of the wavelengths becomes small. Or if a subset of the k's in the 4-point function becomes small as a vector. So here, all the k's are large, but there's sort of a scale here that's becoming long in length. Then large-scale structure becomes very sensitive and is probably ultimately most powerful. That may have been too long. That may have been too long of an answer. Maybe you're asking something more specific.
Well, can you go ahead?
Okay.
Yeah. So your scene-based grading, so do you the algorithm that the black box that you have made, do you need the map to be on this sphere, or suppose you have one person in this spot?
Oh yeah. I see why you're asking that question. Yeah, that would be, I never tried it in a case like that. The way it's formulated, I guess it would end up being quite expensive because we represent the map in a full sky harmonic basis. And so that's going to force you to do like full sky spherical harmonic transforms every time you iterate. So you might find that it runs a factor of 1 or more steps slower or something like that.
So there is no flat simulation.
No. Yeah, if your survey is small enough that you can make the flat sky approximation, then it probably becomes really fast. Because you can use 0 pad by a factor of 2, say, and you get to use. So you don't have a large one of our sky, and you get to use fast Fourier transforms, which are much faster than the rest. I think that it would work.